If you launched the fastest spacecraft humanity has ever built toward Alpha Centauri right now, your grandchildren's grandchildren would still be waiting for it to arrive. And yet, the light from that system, carrying in principle every detail of whatever is happening on any planet orbiting it, is reaching your eyes tonight for free, having crossed 4 light years in 4 years. We simply do not yet know how to read it. Tonight, we go to the nearest star system and find out why we can see the light of a potentially living world, but cannot tell you what it looks like. Before we dive in, if you love exploring the cosmos as much as we do, take a second to like the video or subscribe and tell me where you're listening from and what time it is. Now, let's begin. There is a constellation that belongs, in a sense, to the sea. The ancient Greeks knew parts of it, but they could never quite see it whole. Too far south, too close to the horizon on their darkest Mediterranean nights, its most famous features swimming in the murk at the edge of the sky. The sailors of Polynesia knew it better. The Indian Ocean navigators threading between continents in their lateen-sailed dhows. The Aboriginal astronomers of Australia, who had been mapping the southern sky for tens of thousands of years before anyone else thought to write down what they saw. They all knew this part of the heavens. They all knew the 2 brilliant stars that hang there, close together, unmistakable. They called them by different names in different centuries. We call them Alpha Centauri and Beta Centauri. We call the larger constellation Centaurus, the mythological horseman of ancient Greece. But for most of human history, these 2 stars were simply guides, fixed lights, points of navigation in a universe that did not yet know it had edges. Here is something worth sitting with before we go any further. For the entire span of human civilization, from the first irrigation canals of Mesopotamia to the first moonwalk, those 2 stars were simply beautiful. They were bright, they were dependable, they rose and set with the seasons, and they were assumed to be roughly like every other star, distant, silent, mysterious in a vague and general way. No one knew how far they were. No one had the tools to find out. No one, for most of recorded history, could have told you whether those stars were 1 light year away or 1,000,000. The sky was simply the sky, and its depths were matters for imagination, not measurement. And then, slowly, science arrived. The story of how we came to understand that Alpha Centauri is our nearest stellar neighbor is, in many ways, a story about the limits of human vision, and about what happens when we build instruments that extend those limits beyond what our bodies can achieve. It is a story that begins at the southern tip of Africa, at a rocky promontory where 2 great oceans meet, where the wind is always on you and the nights are often clear. It begins at the Royal Observatory, Cape of Good Hope, perched above a coastline that had already witnessed centuries of the most ambitious navigation in human history. In the early 1830s, a Scottish astronomer named Thomas Henderson arrived at the Cape Observatory to take up a post arranged for him by the British Admiralty, which needed better stellar measurements for maritime navigation. Henderson was not, by most accounts, a particularly content man in South Africa. He found the climate difficult, the post frustrating, and he was eager to return to Edinburgh. But before he left, he did something remarkable. He made a series of extraordinarily careful observations of Alpha Centauri, tracking its apparent position in the sky over many months, building up a dataset of positional measurements so precise that they could, in theory, reveal something that had never been measured before. What Henderson was attempting was a technique called parallax. Here is what that word means in plain terms. Hold up one finger in front of your face, then close one eye, then the other. Notice how your finger seems to jump against the background. That apparent shift, caused by the fact that your two eyes are separated by a few centimeters, is parallax. Now imagine doing that same trick, but instead of two eyes a few centimeters apart, you are using the Earth's position in its orbit around the Sun at 2.6 months apart. The baseline between your two measurement positions is now roughly 300 million kilometers. A nearby star will seem to shift against the background of more distant stars, just slightly by a tiny angle, in a way that reveals, through straightforward geometry, exactly how far away it is. Henderson's measurements of Alpha Centauri suggested that this shift was substantial compared to other stars. It suggested the star was close, extraordinarily close on the cosmic scale. But Henderson was cautious. He didn't trust his data enough to publish. He worried about instrumental errors, about systematic biases in his measurements. He returned to Edinburgh, took up his post as Astronomer Royal for Scotland, and sat on his results. In 1839, he finally published them. By then, the German astronomer Friedrich Bessel had already published a parallax measurement of a different star, 61 Cygni, in 1838, and the Russian astronomer Wilhelm Struve had published a measurement of Vega. But Henderson's measurement of Alpha Centauri, when it finally came, told a story none of the others could match. Alpha Centauri was closer than any star anyone had yet measured. It was, by a significant margin, the nearest star system to our own. The distance implied by Henderson's parallax was roughly 3.25 light-years, a value that modern measurements have refined to 4.24 light-years for the closest component of the system, but which Henderson got approximately right with instruments that would look primitive today. Pause here for a moment, because this number deserves careful attention. 4.24 light-years. A light-year is the distance light travels in a single year, moving at just under 300,000 kilometers per second. In 1 year, light covers roughly 9.46 trillion kilometers. Multiply that by 4.24, and you get a number so large it resists intuition. To put it in terms that the body can almost grasp, if you built a scale model of the solar system where the distance from the Earth to the Sun was 1 meter, a single long stride, then Alpha Centauri would be 272 kilometers away. In that model, the solar system is your kitchen table, and Alpha Centauri is on the other side of a mountain range. The number sounds near. On any human scale, it is not. This is close, on the scale of the galaxy. This is vanishingly, almost uncomfortably close, in the sense that no other star comes nearer to our Sun. But it is still a distance so vast that no human technology has ever come close to bridging it. The fastest spacecraft humanity has ever launched toward interstellar space. The Voyager probes, which left Earth in 1977 and are now in interstellar space, would take approximately 73,000 years to reach Alpha Centauri if they were pointed in the right direction. We are separated from our nearest neighbors by a gulf that, measured in human terms, is effectively infinite. And yet, those two stars are there, every night, visible to the naked eye, burning quietly 4 light-years away. They have been there for every generation of every human being who ever lived. They were there when the first anatomically modern humans walked out of Africa. They were there when the pyramids were built. They were there when the Roman legions marched, and when the printing press was invented, and when the first nuclear reactor was switched on in Chicago in 1942. For all of that time, they were simply stars, beautiful, fixed, unreachable, and assumed to be empty. That assumption is what this story is about. The simple version of Alpha Centauri, and here is where the textbook account starts to show its first cracks, is that it is a single star. You see it as a single point of light. Most star atlases list it as a single entry. Its name sounds singular. But the telescopic reality, known to astronomers since the early 18th century, is considerably more complex. Everyone who has looked at the night sky knows Alpha Centauri as a brilliant point of light. You probably think of it as a star, one star, shining steadily above the southern horizon. That picture, taken on its own, is accurate as far as it goes. But here is what almost nobody tells you when they point out Alpha Centauri for the first time. What looks like one star is actually two stars orbiting each other, locked in a gravitational partnership so intimate that the human eye cannot separate them without magnification. What you see as a single diamond-bright point is in fact two suns circling each other in a slow 80-year waltz, so close together in angular terms that only a telescope reveals the gap between them. Alpha Centauri A and Alpha Centauri B are what astronomers call a binary pair. They are gravitationally bound, meaning that neither star travels freely through space. Instead, they orbit their common center of gravity, the way two dancers might circle each other, held together by nothing but the invisible pull of mutual attraction. Their orbital period, the time it takes them to complete one full revolution around each other, is approximately 80 years. During that 80-year cycle, their apparent separation in the sky changes. At their widest, they are separated by about 22 arcseconds, which is enough to be split by a modest telescope. At their closest approach, they come within about 4 arcseconds of each other, and resolving them requires more careful instrumentation. Alpha Centauri A is the larger of the two. It is a G-type star, the same spectral classification as our own Sun, but slightly more massive, slightly more luminous, slightly larger in diameter. If you placed Alpha Centauri A where our Sun sits, the planets of the solar system would orbit a slightly brighter, slightly warmer star, but the differences would not be dramatic. In fact, of all the known stars in the observable universe, Alpha Centauri A is probably the most Sun-like in its readily measurable properties. It has been burning hydrogen in its core for roughly 5 billion years, slightly longer than our own Sun according to current estimates. And it will continue to do so for several billion years more before beginning the slow swelling transformation into a red giant. Alpha Centauri B is smaller and cooler. It is a K-type star, often called an orange dwarf, with a surface temperature of approximately 5,260 Kelvin compared to Alpha Centauri A's roughly 5,790 Kelvin and the Sun's 5,778 Kelvin. B is about 90% of the Sun's mass and emits roughly half the Sun's total energy output. It is, by any measure, a perfectly stable, long-lived star. In its own way, it is as unremarkable as its partner, which is to say, it is extraordinary precisely because it is so ordinary, so sun-like, so similar to the kind of star that gave rise to everything alive on Earth. The relationship between A and B is intimate on a stellar scale. At their closest approach to each other, they are roughly 11 times the distance from the Earth to the Sun. About 11 astronomical units, or AU. At their farthest, they separate to 36 astronomical units. For comparison, the Sun and Saturn's are about 10 astronomical units apart, and the Sun and Neptune are about 30 astronomical units apart. So, at their closest, A and B are roughly as far apart as the Sun and Saturn. At their farthest, they are like the Sun and Neptune. Both stars are always, by human standards, incomprehensibly far from each other. But in the context of binary star systems, This is a reasonably close gravitational partnership. For a long time, for most of the history of the telescope, this was the whole story of Alpha Centauri, a binary pair of relatively sun-like stars, the nearest to our own solar system, orbiting each other in an 80-year cycle. Beautiful, nearby, and apparently simple. But apparently simple is exactly the kind of description that deserves suspicion. In 1915, working from the Union Observatory in Johannesburg, South Africa, a Scottish-born astronomer named Robert Innes made a discovery that changed the story permanently. Innes was examining photographic plates of the region around Alpha Centauri, comparing images taken at different times to look for stars that moved against the background, a technique called proper motion detection, when he noticed something odd. There was a faint, reddish star near Alpha Centauri that appeared to be moving through the sky at nearly the same rate and in nearly the same direction as Alpha Centauri A and B. This suggested it might be associated with the Alpha Centauri system, sharing its journey through the galaxy. The star was faint, enormously faint, relative to its apparent neighbors. It could not be seen without a telescope, and even through a telescope, it was an undistinguished red smudge compared to the brilliant double star nearby. But Innes measured its position carefully, tracked its movement across the sky, and eventually concluded that it was slightly closer to Earth than Alpha Centauri A and B. Not by much. The difference was small enough to be within the uncertainty of his measurements. But if confirmed, it would mean that this faint red star, not the brilliant double, was the actual nearest star to our Sun. Innes called it Proxima Centauri. Proxima from the Latin word for nearest. The name was almost aggressively functional. This is the star that is closest to us. This is it, right here. And he was right. Subsequent measurements, carried out with increasing precision over the following decades, and confirmed with exquisite accuracy by the European Space Agency's Hipparcos satellite in the 1990s and the Gaia satellite in the 2000s and 2020s, showed that Proxima Centauri is indeed slightly closer to Earth than Alpha Centauri A and B. The current best measurement places Proxima at 4.244 light-years from Earth, compared to 4.37 light-years for the binary pair. The difference is small, about 0.13 light-years, roughly 1.2 trillion kilometers. But it is measurable, and it means that when we talk about our nearest stellar neighbor, we are technically talking about a star that nobody had ever seen until 1915. So here is the picture as the 20th century begins its second decade. Alpha Centauri is a three-star system. Two of those stars, A and B, are bright, sun-like, easily visible to the naked eye, locked in an 80-year binary orbit. The third, Proxima, is faint, red, and hidden from the naked eye, but it is the actual nearest star to our solar system. And whether Proxima is truly gravitationally bound to A and B, or merely passing nearby in a cosmic coincidence, is a question that occupied astronomers from Innes's time through the era of precision satellite astrometry. Take stock of where we are before going deeper. We have a star system that for most of human history appeared to be one or two stars of no particular significance other than their proximity. We have now established that it is three stars. We have established their approximate characters: two sun-like stars in a close binary orbit, and one small dim red star that happens to be the actual nearest to us. We have established that the whole system is profoundly close on the cosmic scale, separated from our solar system by a gap that is nevertheless enormous on any human scale. Now comes the question that everything else depends on. Do any of these three stars have planets? Proxima Centauri is, by nearly every measure, the opposite of what you might expect the nearest star to our Sun to be. When people learn that Proxima is our nearest stellar neighbor, the intuitive expectation is that it must be something like our Sun. After all, we found it by looking toward a part of the sky that contains two very Sun-like stars. If the cosmos distributes stars of varying types in a roughly random pattern, then the nearest one might reasonably be expected to resemble something familiar. The history of astronomy has tended to reinforce that expectation. The stars we noticed first, the bright ones that caught our ancestors' attention, were mostly stars of similar type to the Sun, because similar type stars tend to be brighter and therefore more noticeable. But that picture is almost entirely wrong when applied to the actual population of stars in the galaxy. Proxima Centauri is proof of that wrongness. Proxima is what astronomers classify as an M-type main sequence star, a red dwarf. Red dwarfs are by far the most common type of star in the Milky Way. Estimates suggest that somewhere between 70 and 80% of all stars in our galaxy are red dwarfs. They are not the spectacular giants that burn bright and die young. They are not the yellow-white middleweights like the Sun. They are small, dim, red, and extraordinarily long-lived. Proxima Centauri, for all its unassuming appearance, will burn hydrogen in its core for roughly 4 trillion years. To put that in perspective, the universe itself is only 13.8 billion years old. The Sun will exhaust its hydrogen fuel in roughly another 5 billion years. Proxima will still be burning, quietly and steadily, when the Sun has long since swelled into a red giant, consumed its inner planets, and collapsed into a white dwarf cooling in the dark. When the universe is roughly 300 times its current age, Proxima Centauri will still be alive. Proxima's mass is roughly 12% of the Sun's. Its diameter is about 15% of the Sun's. In terms of visible light output, it is only about 0.0017 times as luminous as the Sun. Which is to say, if you stood at the same distance from Proxima as the Earth stands from the Sun, you would receive roughly 1/6% of the sunlight we normally receive. The sky above such a planet would be dim, even at noon. The star would appear as a large reddish disk, larger than our Sun appears from Earth, because a habitable planet would need to orbit much closer to capture enough warmth. But its light would be deeply reddish-orange, rich in infrared wavelengths, deficient in the blue-white brightness that defines our experience of daylight. None of this is particularly alarming on its face. Many types of stars host planets. Many types of stars could, in theory, support life if the conditions were right. The fact that Proxima is dim and red does not automatically preclude habitable planets in its vicinity. In fact, by some arguments, the extraordinary longevity of red dwarf stars makes them more intriguing hosts for life than Sun-like stars. Life on Earth took roughly 4 billion years to evolve from single-celled organisms to complex multicellular creatures. A planet orbiting a red dwarf has 4 trillion years to experiment with chemistry. That is 1,000 times the time Earth had. This argument has been made seriously and carefully by researchers working in astrobiology, the scientific study of life's potential distribution in the universe. It is not fringe speculation. It is a genuine and active consideration. But here is where the story of Proxima Centauri becomes genuinely complicated, and where the comfortable narrative of the nearest habitable world starts to acquire edges. Proxima is not merely dim and red. It is also violent in a way that Sun-like stars are not, and that violence has profound implications for anything trying to survive within range of it. Red dwarf stars like Proxima are magnetically active in ways that are disproportionate to their size. The physics of this is rooted in how energy moves from a star's interior to its surface. In the Sun, the outer layers convect. Hot plasma rises, cools, and sinks back down in large but organized circulation cells. In a fully convective red dwarf like Proxima, the entire star convects as a single turbulent system, from core to surface without interruption. This full-body convection generates a magnetic field that is, relative to the star's size, far more powerful than the Sun's magnetic field. And powerful magnetic fields means strong magnetic activity. And strong magnetic activity means flares. Solar flares are bursts of electromagnetic radiation, X-rays, ultraviolet light, radio waves, released when twisted magnetic field lines in the Sun's atmosphere suddenly snap and reconnect. They happen on the Sun, and they affect Earth. They can disrupt satellite communications, damage power grids in extreme cases, and produce spectacular auroral displays. But the Sun's flares are, in the context of the stellar neighborhood, relatively mild. The Sun is a magnetically quiet star. Proxima Centauri is not. Proxima produces flares that are, by the standards of our Sun, extreme. Observing campaigns in 2016 and subsequent years documented flare events in which the star's ultraviolet output increased by factors of hundreds within seconds. There is a recorded event, captured in 2019 by a team of researchers using multiple telescopes in coordination, in which Proxima increased its ultraviolet brightness by roughly 14,000 times its normal output over a period of just a few seconds. 14,000 times. Not 14% more. Not 14 times more. 14,000 times more in the time it takes to finish a sentence. This matters enormously for any planet in Proxima's vicinity, for reasons we will examine in detail. For now, hold this image. A small, dim star, burning with a quiet red glow, suddenly erupting in a paroxysm of ultraviolet radiation, so intense it would dwarf anything our Sun is capable of producing. And this does not happen once a decade, not once a year, but potentially dozens of times a day. The nearest star to the Sun is a flare star, a violent, magnetically hyperactive flare star. Before moving forward, it is worth asking a question that turns out to have a surprisingly uncertain answer. Is Proxima Centauri actually part of the Alpha Centauri system, or is it merely a passing neighbor? This question has been debated since Innes identified Proxima in 1915. The fact that Proxima moves through the sky at nearly the same speed and in nearly the same direction as Alpha Centauri A and B suggests an association. They appear to share a common motion through the galaxy, which would be consistent with a gravitational bond. But consistent with is not the same as proof. For stars to be genuinely gravitationally bound, Proxima's velocity relative to A and B must be less than the escape velocity at its current distance from them. Calculating this requires knowing the star's velocities with extraordinary precision. For decades, the question was genuinely open. The Hipparcos satellite's measurements in the 1990s improved the picture somewhat, and the Gaia satellite's precision in the 2010s and 2020s has helped further. The current best estimate suggests that Proxima is very likely, though not certainly, gravitationally bound to Alpha Centauri A and B, orbiting the pair at a distance of roughly 0.21 light-years on an orbital period of somewhere between 500,000 and 600,000 years. It is a vast, lonely orbit, taking Proxima in a slow loop around its brilliant partners at a distance so great that those partners appear as extremely bright stars from Proxima's perspective, rather than surrounding presences. This uncertainty, very likely but not certainly, is itself a scientific detail worth noting. We are talking about the nearest star system to the Sun, studied intensively for over a century, and we still cannot say with complete certainty whether its three stars are bound to each other. This is not a failure of science. It is a window into what science actually is, a process of progressively reducing uncertainty, arriving at, very likely as a considered position, that will, with more data, eventually become either virtually certain or possibly be overturned entirely. The universe does not offer easy answers. It offers data, and we interpret what we can. Proxima orbits at a vast distance. Proxima burns with violent light. Proxima is the closest star to our home, and it is nothing like we expected. Now we turn to the question that consumed astronomers for decades before it finally produced an answer: the question of planets. The search for planets around Alpha Centauri did not begin with Proxima. It began with the obvious candidates, Alpha Centauri A and B, because they were the most sun-like stars in the nearest system, and planet hunters initially focused their attention on sun-like stars. The reasoning was intuitive. If the goal was to find something familiar, the search should begin around something familiar. The technique most commonly used in the early era of exoplanet discovery was what astronomers call the radial velocity method. Stripped of jargon, here is what it means. If a planet orbits a star, the planet's gravity tugs on the star, just as the star's gravity tugs on the planet. The planet pulls the star toward itself as it orbits, causing the star to wobble slightly, not to move dramatically through space, but to shift back and forth in a tiny dance, moving toward us and then away from us as the planet completes each orbit. When a star moves toward us, its light gets compressed slightly, shifted toward the blue end of the spectrum. When it moves away, its light gets stretched slightly, shifted toward the red. This shifting of the star's light, the Doppler effect, can be measured with a sufficiently precise spectrograph, and the pattern of shifting reveals the presence of a planet, its orbital period, its minimum mass, and sometimes a rough estimate of its distance from the star. The radial velocity method had a triumphant moment in 1995 when Swiss astronomers Michael Mayor and Didier Queloz announced the detection of the first planet around a sun-like star, a massive world called 51 Pegasi b, orbiting its star so closely that its year lasted only 4.2 days. Mayor and Queloz, working at the Haute-Provence Observatory in France, had achieved what astronomers had been attempting for decades: a confirmed exoplanet detection that could be independently verified. They were awarded the Nobel Prize in Physics in 2019. Their success set off a gold rush in planet hunting that continues unabated. It seemed natural in the years following 1995 that Alpha Centauri would be among the first and most richly rewarded targets of the expanding planet hunting enterprise. It was the nearest star system. It contained two sun-like stars. If any nearby system harbored planets, surely it would be this one. And yet, for many years, Alpha Centauri A and B proved frustratingly uncooperative. The problem is geometric and fundamental. Alpha Centauri A and B are in a relatively close binary orbit. When you try to measure tiny Doppler shifts in one star's light, the tiny wobbles caused by a planet, you also have to carefully account for the much larger wobble caused by the gravitational pull of the stellar companion. Disentangling a small planetary signal from a large stellar binary signal requires extraordinary precision, extraordinary patience, and extensive careful modeling. For years, no one could extract a clean answer. Surveys ran. Spectrographs stared at Alpha Centauri night after night. The results kept coming back ambiguous. Then, in October 2012, a team led by Swiss astronomer Xavier Dumusc, working with the HARP spectrograph at the La Silla Observatory in the Atacama Desert of Chile, one of the most sensitive planet-finding instruments ever built at that time, announced a result that briefly electrified the astronomy world. They reported the detection of a planet orbiting Alpha Centauri b. The planet was designated Alpha Centauri bb. It had an orbital period of just 3.2 days, placing it in an orbit far closer to Alpha Centauri b than Mercury is to our Sun. It was likely rocky. It had a minimum mass comparable to Earth's. The announcement made headlines worldwide. The nearest star system to Earth appeared to contain a planet. Our nearest neighbor had a world. And though Alpha Centauri bb was far too close to its star to be anywhere near habitable, the temperatures on its surface would have been measured in the thousands of degrees. The detection seemed to open a door. If there was one planet around Alpha Centauri b, there could be more. There could be planets farther out, cooler and potentially temperate. The excitement was real. It was understandable. But here is what that initial celebration did not account for. Over the following years, as other researchers examined the HARP's data more carefully, and as new datasets accumulated, serious doubts emerged about the Dumusc detection. The signal that had been interpreted as a planet was small, right at the edge of what the instrument could detect. Some researchers began to argue that the signal might not be a planet at all. It might be an artifact, a false signal produced by the way stellar activity on Alpha Centauri b's surface, the rising and falling of convective cells, the subtle brightening and dimming caused by star spots, mimicked the Doppler signature of a planet. In 2015, a reanalysis concluded that the planetary signal could not be confirmed. In 2015, a comprehensive re-examination led by Vinesh Rajpal and collaborators at the University of Oxford, using far more sophisticated modeling techniques, concluded that there was insufficient evidence for the existence of Alpha Centauri bb. The planet was not announced as disproved. Science rarely works that way. What happened instead was a gradual, careful, painful retreat from certainty. We cannot confirm this planet. The signal may be stellar activity. More data is needed. The world that had briefly seemed to announce itself from the nearest binary star receded into statistical noise. This is, in its own way, a fundamental lesson about the practice of science. Detection is hard. The universe does not reveal itself clearly. The signals we seek, the tiny wobbles of a star pulled by an orbiting planet, are so small, so easily confused with other phenomena, that the history of exoplanet science is littered with candidates that rose and fell, detections that were celebrated and then quietly abandoned. This does not mean that planet hunting is unreliable. The field has produced thousands of confirmed exoplanets, many resting on independent lines of evidence that reinforce each other. The science is robust in aggregate, even if individual detections sometimes require revision. But the story of Alpha Centauri bb, a planet found and then lost, a world that existed briefly in the imagination before dissolving back into the noise, is a story that matters. It matters because it reminds us how hard this is. It matters because the story is not over. And it matters, most of all, because while astronomers were arguing about whether Alpha Centauri b had a planet, a very different and more compelling discovery was quietly building in the data. It was coming from Proxima Centauri. The discovery of Proxima b was not a single moment. It was, like most of the best discoveries in astronomy, the result of years of patient accumulation. Data taken on quiet nights at remote observatories, spectra analyzed and reanalyzed, instrumental artifacts painstakingly characterized, and a signal so small that it took the combination of multiple independent datasets before it could be taken seriously. The team that ultimately brought Proxima b to the world was led by Guillem Anglada Escudé, a Spanish-born astronomer then based at Queen Mary University of London. Anglada Escudé had been working with HARPS data from the European Southern Observatory's La Silla site in Chile for years, and he had become convinced that Proxima Centauri deserved a far more intensive and coordinated observing campaign than it had previously received. In 2016, he organized what was called the Pale Red Dot campaign, named in deliberate echo of Carl Sagan's famous pale blue dot description of Earth as seen from deep space. The campaign was unprecedented in its design, a concentrated, coordinated multi-telescope push on Proxima Centauri, running from January to April of 2016, combined with archival data from earlier HARPS observations. The result was a radial velocity signal of unmistakable regularity. Proxima Centauri was wobbling. Not dramatically. The wobble amounted to a velocity shift of about 1.38 meters per second, roughly walking pace. But it was there, and it repeated with clockwork regularity over a period of 11.2 days. In August 2016, Anglada Escudé's team published their findings in the journal Nature. Proxima Centauri had a planet. The planet was designated Proxima Centauri b, or simply Proxima b. From what the radial velocity method could tell the team, it had a minimum mass of roughly 1.27 Earth masses, placing it in the category of what astronomers call a super-Earth or a roughly Earth mass world, depending on the true inclination of its orbit. Because the radial velocity method only measures the component of a star's motion directed toward or away from the observer, the true mass of the planet depends on the orbital geometry. If the orbit is edge-on to our line of sight, the measured velocity shift is the maximum, and the mass estimate is at its minimum. If the orbit is tilted, the actual mass could be higher. Estimates suggest that the most likely scenario places Proxima b's true mass at somewhere between 1.3 and 2.5 Earth masses. Critically, Proxima b's orbital period of 11.2 days places it at a distance of about 0.0485 astronomical units from Proxima, roughly a 20th of the Earth-Sun distance. This sounds catastrophically close. In our solar system, a planet at that distance from the Sun would be scorched rock, far inside the orbit of Mercury, in a region of temperatures measured in hundreds of degrees Celsius. But Proxima is not our Sun. Proxima is enormously less luminous. At 0.0485 astronomical units from such a dim star, a planet receives roughly 70% of the energy flux that Earth receives from the Sun. This places it within what astronomers call the habitable zone. The habitable zone deserves careful attention because its name can be misleading. When astronomers say habitable zone, they mean a specific, calculable range of orbital distances around a given star where the energy input from that star would be, by itself, sufficient to maintain liquid water on a rocky planetary surface, assuming an Earth-like atmosphere. It is not a guarantee of habitability. It is not a claim that life exists there. It is one necessary condition among many. A planet can be in the habitable zone and still be bone dry, or covered in ice, or wrapped in an atmosphere of sulfuric acid. Mars is near the inner edge of the Sun's habitable zone. Venus is also within or near the habitable zone by some definitions. One is a freezing desert. The other is a 465-degree cauldron with surface pressure 90 times higher than Earth's. But the habitable zone is still meaningful. A planet outside it, too close to its star or too far away, faces energetic challenges to liquid water that are purely physical and absolute. A planet inside the habitable zone at least has a chance. And Proxima b, as best as the data of 2016 could establish, was inside the habitable zone of its star. This was not a small discovery. This was, arguably, one of the most significant announcements in the history of astronomy. Not because it proved that life exists on Proxima b, it proved no such thing, but because it revealed that our nearest stellar neighbor, the star closest to the Sun, the star just 4.24 light-years away, has a world in the temperature range where water could be liquid. A world where, if you had an Earth-like atmosphere and an Earth-like composition, water could pool on the surface. Anglada Escudé himself was careful to hedge in the paper and in subsequent public statements. The radial velocity method tells you the planet is there, but it tells you almost nothing about the planet's nature. It cannot tell you whether the planet has an atmosphere. It cannot tell you whether it has water. It cannot tell you whether its surface looks anything like what we mean by a planetary surface. What it tells you is, there is a gravitationally significant body orbiting Proxima Centauri every 11.2 days, and its mass is probably not dramatically different from Earth's. That is the foundation. Everything else is extrapolation. In 2020, a second planetary candidate around Proxima was tentatively announced, designated Proxima c, with an orbital period of roughly 5 years and a much larger orbital distance. At that distance, even Proxima's feeble heat would leave the planet in permanent deep freeze, well outside the habitable zone. Proxima c's detection has remained disputed, with some analyses supporting it and others finding the signal too ambiguous to confirm. A third candidate, Proxima d, was proposed in 2022, based on an even more subtle velocity signal, with an orbital period of only about 5 days, placing it even closer to Proxima than Proxima b, and even more certainly outside any meaningful habitable zone. The picture, as of current knowledge, is something like this. Proxima Centauri very probably has at least one confirmed planet, and possibly 2 or 3 more. The confirmed one sits in the habitable zone. The others, to the extent they exist at all, are likely frozen wastelands or scorched rocks. None of the candidates have been directly observed. None have had their atmospheres characterized. None have had their surfaces imaged. They are inferences drawn from the way their star wobbles, nothing more. And that wobble, that 1.38 meter per second sway in Proxima's radial velocity, is all we have. Everything that matters about Proxima b, everything that determines whether it is alive or dead, warm or frozen, welcoming or hostile, lies hidden behind 4.24 light-years of empty space, beyond the reach of any instrument currently in operation or currently planned. Stay with that for a moment. Our nearest star system has a world in its habitable zone, and we cannot tell you what that world looks like. We cannot tell you its color. We cannot tell you whether its sky holds clouds or is bare rock and vacuum. We cannot tell you if anything moves on it. Here is where the apparent simplicity of the Proxima b story begins to collapse. You have been told, or you might have assumed, from the coverage of this discovery in Science News, that Proxima b is a potentially habitable world, a rocky planet in the habitable zone of its star, mass comparable to Earth's, right next door on the cosmic scale. The narrative almost writes itself. Humanity's nearest neighbor has an Earth-like world, and perhaps, just perhaps, something lives there. That picture is seductive. But here is what the textbook summary doesn't tell you, and here is what makes Proxima's situation genuinely and deeply complicated. Proxima is not only a habitable zone provider, It is simultaneously an extraordinarily efficient destroyer of everything that makes a habitable zone meaningful. Red dwarf stars like Proxima are magnetically volatile in a way that Sun-like stars are not. And this volatility is not incidental. It is structural. It is baked into the physics of how these stars operate. The full convective circulation of the stellar plasma generates tangled, powerful magnetic field lines that periodically snap and reconnect in explosive events called stellar flares. On the Sun, flares are notable events. The most powerful ones, called X-class flares, can affect satellite communications and have, in rare extreme cases, disrupted power grids. In November 2003, a severe solar flare caused radio blackouts across much of the planet. These events are disruptive, and particularly powerful ones happen perhaps a handful of times per decade. On Proxima Centauri, flares happen all the time. Multiple observing campaigns have documented dozens of flare events per day on Proxima, including frequent events far more energetic than the most powerful solar flares ever recorded. In March 2016, right in the middle of the pale red dot campaign that would later announce Proxima b, an enormous flare erupted from Proxima, increasing the star's overall brightness by approximately a factor of 100, briefly making it visible to the naked eye from dark sites. The ultraviolet component alone increased by a factor of several hundred. The 2019 event, in which the ultraviolet brightness rose by 14,000 times normal output in seconds, represents the kind of stellar violence that would, on a geologically regular basis, wash over any planet in Proxima's immediate vicinity. Ultraviolet radiation is particularly relevant to the habitability question because of what it does to atmospheres and to biology. Earth is protected from its sun's ultraviolet output by two complementary systems. First, Earth has a magnetic field generated by its liquid iron outer core, a magnetosphere that deflects most of the energetic charged particles in the solar wind, preventing them from stripping the upper atmosphere. Second, Earth has an ozone layer, a thin shield of ozone molecules in the stratosphere that absorbs ultraviolet radiation before it reaches the surface. These two protections work together, and life on Earth has evolved to depend on both. A planet orbiting Proxima faces a different situation. Proxima's flares do not merely emit ultraviolet radiation. They also expel enormous quantities of energetic charged particles, protons, electrons, and heavier ions, in what are called coronal mass ejections, or CMEs. A coronal mass ejection is a burst of magnetized plasma fired off the star's surface, traveling at speeds of hundreds to thousands of kilometers per second. On Earth, the most powerful solar CMEs can compress our magnetosphere, trigger geomagnetic storms, and damage satellites. Proxima's CMEs would be, by comparison, devastating. Here is the core of the problem. A planet in Proxima's habitable zone, like Proxima b at 0.0485 astronomical units, is roughly 20 times closer to its star than Earth is to the Sun. At that distance, the flux of energetic particles during a CME is not 20 times higher than Earth's experience. Particle flux falls off with the square of the distance, so being 20 times closer means the particle flux is 400 times higher. During a flare-associated CME from Proxima, and the most powerful flares are frequently accompanied by CMEs, a planet in the habitable zone would experience a storm of energetic particles at 400 times the intensity that Earth experiences during the worst solar geomagnetic events. For Proxima b to retain its atmosphere under this bombardment, it would need either an extremely powerful magnetic field, far stronger than Earth's, or an extremely dense atmosphere, far denser than Earth's, or both. Without such protection, repeated CME impacts would gradually strip the atmosphere away. The physics of this is well understood. Energetic particles ionize the upper atmosphere, allow atmospheric molecules to be carried away on the stellar wind, and gradually deplete even a thick atmosphere over geological timescales. Mars, which lost most of its once thicker atmosphere billions of years ago, partly through similar processes, in Mars's case primarily through the normal solar wind, not flares, provides a cautionary example of how this unfolds. Some researchers have argued that Proxima b might be able to maintain an atmosphere despite the stellar activity. The argument runs roughly as follows. Volcanic outgassing on a geologically active world continuously replenishes atmospheric gases, and a sufficiently massive planet with a sufficiently active interior might offset atmospheric loss with volcanic input. This is not an impossible scenario, but it would require a very specific set of circumstances, a planet volcanically active enough to compensate for the loss, but not so volcanically active as to create a thick, Venus-like greenhouse atmosphere. And whether Proxima b satisfies those circumstances is fundamentally unknown. Other researchers have proposed a different defense: water. If Proxima b formed beyond the so-called snow line of its protoplanetary disk, the distance at which water ice is stable, and then migrated inward to its current orbit, it might have accreted substantial quantities of water ice, eventually becoming a water world with a deep global ocean. A deep ocean can buffer temperature extremes and is difficult to strip away entirely. But a water world Proxima b would likely have no significant land surface, no continental weathering cycle, and very different chemistry from Earth. And whether it could support life of any kind is a separate question entirely. The honest position, the one the evidence actually supports, is that we do not know whether Proxima b has an atmosphere. We do not know whether it has liquid water. We do not know whether its surface, if it has one, bears any resemblance to a habitable world. These are not minor uncertainties at the edges of an otherwise clear picture. They are the central questions, and they are currently unanswerable. There is a second challenge to Proxima b's habitability that is equally fundamental, and which brings us to one of the more disorienting concepts in planetary science. Picture yourself standing on a planet in the habitable zone of a red dwarf. The star above you is large and reddish, filling more of the sky than our sun fills from Earth's surface. Its light is amber-toned, almost warm to the eye, casting long shadows across a landscape that might be rocky or oceanic or somewhere in between. You stand there for an hour, for a day, for a year. You watch the sky. The other stars rise and set, wheeling slowly overhead as the planet rotates. But the red star stays exactly where it is. It doesn't move, not by a degree, not by a fraction of a degree. This is tidal locking, and it is almost certainly the condition of Proxima b. Tidal locking is the same process that has given the Moon its well-known peculiarity. The Moon always shows us the same face because its rotation rate has been slowed and synchronized with its orbital period by billions of years of tidal friction. The Moon orbits Earth once every 27.3 days, and it rotates on its own axis once every 27.3 days, a perfect synchrony imposed by tidal forces. The side facing Earth has been facing Earth for billions of years. The far side has never been directly visible from Earth's surface. The same physics operates between planets and their stars. The smaller the orbital distance, the more powerful the tidal forces, and the shorter the time before a planet becomes tidally locked. For a planet at Earth's distance from a sun-like star, tidal locking would take many billions of years. longer than the current age of the solar system. But for a planet at Proxima b's distance from Proxima, 20 times closer than Earth is to the Sun, tidal locking would occur within a few 100 million years at most. Given that the Proxima Centauri system is estimated to be at least 4 billion years old, Proxima b has had ample time to become fully tidally locked. If Proxima b is tidally locked, it has a permanent day side and a permanent night side. The day side faces the star always. It receives the star's warmth, its radiation, its occasional devastating flares, without pause or seasonal relief. The night side faces away from the star into the perpetual cold of space, receiving no direct stellar energy at all. The temperature difference between the two hemispheres could be extreme. Some models suggest temperature contrasts of hundreds of degrees Celsius between the warmest point on the day side and the coldest point on the night side. In the early days of exoplanet science, tidal locking was seen as essentially fatal to the idea of habitable planets around red dwarfs. The argument was straightforward. The night side would freeze everything, including the atmosphere itself. All the air would condense and fall as ice on the cold side, leaving the day side airless and the night side buried under a frozen layer of what had once been atmosphere. A tidally locked planet in this vision would have no functional climate system, no moderate temperatures, and no liquid water. But this early assessment turned out to be too pessimistic. As climate modelers began applying sophisticated general circulation models to tidally locked planets, the same type of computer models used to simulate Earth's climate, a more nuanced picture emerged. A planet with a sufficiently dense atmosphere would have winds. Powerful winds driven by the extreme temperature gradient between day and night sides. Those winds would carry heat from the day side to the night side, moderating the temperature difference, preventing the complete collapse of the atmosphere onto the cold side. In some models, a tidally locked planet around a red dwarf could maintain moderate temperatures in a broad terminator zone, the region at the boundary between permanent day and permanent night, and possibly even in a crescent of moderate climate on the night side, warmed by wind-carried heat. This is not a comfortable world to imagine by any standard we would recognize. There would be no sunrises or sunsets. The star would be fixed in one part of the sky for the entire life of the planet. There would be no seasons in any sense meaningful to us. The weather patterns would be alien, enormous, permanent storm systems anchored to the point directly beneath the star on the day side, cold, dark atmospheric rivers on the night side, a narrow, potentially temperate zone at the terminator where the planet's edge faces toward and away from the star simultaneously. If you could stand at the right latitude at the permanent boundary between day and night, you might see the star hanging eternally just above the horizon, a red disk, large and steady, never rising, never setting, casting a permanent twilight across the world. Some climate models actually find such a world could be surprisingly temperate. Studies from research groups, including those at the University of Exeter, have found that for a range of atmospheric conditions, a tidally locked rocky world in Proxima's habitable zone could maintain surface temperatures, permitting liquid water over a significant fraction of its surface. This is not a guarantee, but it is not impossible. The fundamental reality is this: we do not know if Proxima b is tidally locked. The radial velocity method that detected it cannot determine rotation state. We do not know if it has an atmosphere. We do not know its surface composition, its internal structure, or its geological activity. Every statement about Proxima b's potential habitability is a model, a computer simulation run with a set of assumed conditions. And the conditions themselves are almost entirely unconstrained. Different assumptions produce wildly different outcomes. Some models say Proxima b could be habitable. Others say it is a dead rock. Others say it could be a global ocean, or an ice world, or an airless stone orbiting a flare star in permanent silence. We are debating the characteristics of a world we cannot see, around a star we cannot visit, using instruments that were not designed to answer the questions we are most urgently asking. We cannot see Proxima b's surface. We cannot test whether it has air. We cannot stand in its light, which may or may not fall on liquid water, which may or may not surround anything alive, which may or may not know, in whatever language chemistry allows, that somewhere 4 light years away, a small planet is asking about it. While Proxima has dominated the planetary discussion, it would be a mistake to overlook what might orbit its brilliant partners. Alpha Centauri A and B have not been forgotten by planet hunters, and the story of what might exist around those 2 sun-like stars is worth following carefully. The story begins, as we saw, with disappointment. The 2012 claim of a planet around Alpha Centauri b proved, on closer examination, to be unconfirmed. But the failure to confirm one planetary candidate does not preclude others. The absence of a detection is not the same as a confirmed absence. The question of whether A and B could host habitable planets touches on orbital mechanics in ways that are illuminating. Because A and B are a binary pair, any planet orbiting one of them must maintain a stable orbit against the gravitational perturbations of the other. Numerical simulations have shown that stable planetary orbits are possible around each star individually, provided the planets remain within a certain critical radius, roughly 3 astronomical units for planets orbiting A alone, and roughly 2.5 astronomical units for planets orbiting B alone. Beyond those distances, the gravitational perturbations from the binary companion would destabilize orbits over geological timescales. 3 astronomical units from Alpha Centauri A, 2.5 astronomical units from Alpha Centauri B. The habitable zone of Alpha Centauri A, defined by its slightly higher luminosity, sits at roughly 1.2 astronomical units, comfortably within the stable zone. The habitable zone of Alpha Centauri B sits at roughly 0.75 astronomical units, also within the stable zone. In principle, both stars could harbor habitable zone planets with gravitationally stable orbits. The binary configuration does not, by itself, preclude planets in the liquid water zone around either star. The difficulty remains detection. Alpha Centauri A and B are much brighter than Proxima, which makes them easier to observe in some respects. But the presence of the stellar companion makes extracting clean radial velocity measurements harder. The stellar activity of A and B, particularly activity-induced velocity signals from surface convection, also complicates the extraction of planetary signals. Several research groups have looked for planets around A and B with various instruments, and some have published tentative candidates over the years. As of late 2025, the James Webb Space Telescope reported strong evidence for a candidate gas giant orbiting Alpha Centauri A, but it remains unconfirmed pending further observations. The most promising near-term avenue for detecting planets around Alpha Centauri A or B is a technique called direct imaging, essentially taking a photograph of the planet rather than inferring its presence from the star's wobble. This sounds straightforward, but is extraordinarily difficult because the star is so much brighter than the planet that the planet's light is completely overwhelmed. The contrast ratio between a star and an Earth-like planet in reflected light is roughly 10 billion to 1, separating a signal 1/10 billionth as bright as the star from the star itself requires coronagraph technology, instruments designed to suppress the star's light of extraordinary precision. In 2014, researchers proposed a mission to NASA's Small Explorer program called the Alpha Centauri Exoplanet Satellite, ASA-SAT, a small space telescope with a coronagraph designed specifically to look for planets around Alpha Centauri A and B. The concept is not yet funded or approved, but it represents the kind of targeted, purpose-built instrument that the question genuinely deserves. Meanwhile, the European Southern Observatory's extremely large telescope, currently under construction on Cerro Armazones in the Atacama Desert of Chile at an altitude of 3,046 meters, will be, when completed, the most powerful optical telescope ever built, with a primary mirror 39 meters across. Alpha Centauri will almost certainly be among its most frequently revisited targets. The timeline for full operation is currently anticipated sometime in the late 2020s, though large telescope projects have a history of schedule evolution. So the planet question around A and B remains genuinely open. Some researchers have argued that the time to build targeted instruments specifically for Alpha Centauri is now, not later. Their argument is essentially philosophical as well as scientific. This is the nearest star system. If we are serious about the question of life beyond Earth, we cannot indefinitely defer the search on grounds of technical difficulty. The difficulty is real, but so is the prize. The nearest star system, in its entirety, has given us one probable planet around the nearest star, a faint and violent red dwarf. The suggestion of other planets unconfirmed, and two sun-like stars whose potential planetary systems remain stubbornly hidden. 3 stars, each presenting a different kind of problem, each concealing something different behind the veil of distance. The nearest star that resembles our Sun might have planets. The nearest star we can currently confirm has a planet is nothing like our Sun. Now we turn to a question that sounds like a child's question, but turns out to have deeply unsettling answers. How do you get there? 4 light years, 40.2 trillion kilometers, 268,000 times the distance from the Earth to the Sun. The number is so large that it resists compression into anything meaningful. To build a sense of what it actually means, not by comparing one large number to another, but by thinking about time measured in human lives and human generations. The fastest object humanity has ever launched, the Parker Solar Probe, at its closest approach to the Sun, achieves speeds of roughly 692,000 kilometers per hour. At that speed, the Parker Solar Probe would take approximately 6,600 years to travel 4 light years. That is 66 centuries. That is the entire span from the construction of Stonehenge to right now, plus 4,000 more years on top. The Voyager 1 spacecraft, launched in 1977 and currently moving at about 61,200 kilometers per hour relative to the Sun, would take roughly 73,000 years to travel the distance to Alpha Centauri, if it were pointed that way, which it is not. 73,000 years is longer than the time since modern humans left Africa to populate the rest of the planet. Even the most optimistic concepts for near-future interstellar propulsion, nuclear pulse propulsion, where a spacecraft rides a series of nuclear explosions to achieve high velocities. Fusion propulsion, where controlled hydrogen fusion generates a jet of plasma. Ramjet designs that would theoretically scoop interstellar hydrogen and burn it, run up against fundamental engineering constraints. The most ambitious nuclear pulse concept, Project Orion, studied by Freeman Dyson and others in the late 1950s and early 1960s, might theoretically achieve somewhere between 1 and 10% of the speed of light. At 1% of the speed of light, roughly 3,000 kilometers per second, You would reach Alpha Centauri in about 424 years. At 10% of the speed of light, about 42 years. 42 years is within a human lifetime. It is the kind of number that starts to sound conceivable, even if the engineering to achieve it remains fantastically beyond anything currently possible. This calculation sits at the heart of Breakthrough Starshot, an initiative announced in April 2016 by investor Yuri Milner at a press conference where physicist Stephen Hawking appeared alongside him to lend support. The concept, which has attracted both serious scientific attention and profound skepticism, proposes sending not a large crude spacecraft, but an array of gram-scale nanocraft, tiny, lightweight probes attached to laser sail membranes, accelerated by a ground-based array of powerful lasers to about 20% of the speed of light. At 20% of the speed of light, the journey to Alpha Centauri would take roughly 20 years. The nanocraft would fly through the Alpha Centauri system. They cannot break, since at 1/5 the speed of light there is no realistic way to decelerate and enter orbit, and transmit what they observe back to Earth, with the signal taking 4 years to return. The challenges facing Breakthrough Starshot are staggering, and the initiative's own scientific advisors have been candid about this. Accelerating a gram-scale sail to 20% of the speed of light requires a laser array of at least 100 gigawatts of power, roughly the output of 100 nuclear power plants, focused into a single coherent beam and fired for minutes. The precision required to keep such a beam focused on a sail a meter across, over thousands of kilometers of acceleration, exceeds any current technology by orders of magnitude. The nanocraft must survive the interstellar medium, a sparse but real environment of gas, dust, and cosmic rays, at velocities where even a single dust grain would strike it with the energy of a substantial explosive. The sail material must reflect rather than absorb the acceleration laser without burning. The electronics aboard must survive the journey. The signal from 4 light years must be detectable back on Earth. None of these problems are believed to be fundamentally impossible by the physicists and engineers who study them seriously. But not fundamentally impossible is a long way from "we know how to do this." Breakthrough Starshot, in its originally conceived form, would require several decades of fundamental engineering progress before becoming feasible, and would cost tens of billions of dollars even after the necessary technology exists. It is a concept, not yet a mission, a roadmap without a vehicle. And yet, it matters philosophically. For the entire history of the space age, from Sputnik in 1957 through the Apollo program, through the robotic exploration of the solar system, through the era of space telescopes, interstellar space has been treated as genuinely unreachable. The stars are there, we can study them with light, but we cannot go to them. Breakthrough Starshot, even as a concept, begins to crack that assumption. It suggests that the physics allows a path, even if the engineering does not yet exist to walk it. There is another approach to getting there that deserves mention, though it is more speculative in a different direction. Rather than sending something physical, could we instead detect signals from any civilization that already exists at Alpha Centauri? This brings us to a different set of questions entirely. Not how we get there, but whether anything there is trying to reach us, or whether we are reaching towards something that does not yet know we exist. SETI, the search for extraterrestrial intelligence, has not ignored Alpha Centauri. The nearest star system has been on the target list of radio telescope surveys since the field's earliest days, including Project Phoenix observations at Australia's Parkes Observatory beginning in 1995, none of which yielded confirmed signals of artificial origin. More recently, a signal designated BLC1, Breakthrough Listen Candidate 1, was recorded in 2019 by the Parkes telescope while it was pointed at Proxima Centauri and was publicly reported in late 2020. The signal appeared only when the telescope was pointed at Proxima at a specific radio frequency, and it initially passed several tests for a non-natural origin. It generated significant scientific and popular excitement. Then it was traced to terrestrial interference. Again, this is by now a familiar pattern in SETI research. Interesting signals appear, generate excitement, and resolve into human-made radio noise. The challenge of demonstrating that a signal is genuinely not of human origin, not an artifact of a malfunctioning instrument, not an atmospheric or ionospheric phenomenon, is enormous. The history of SETI is not, so far, a history of finding alien signals. It is a history of finding and eliminating false positives, one by one, year by year, building a case through absence. Here is where the apparent simplicity of the detection question needs to be examined directly. You probably think that detecting signs of life on a planet just 4.244 light-years away should be, at this point in human technological development, within our grasp. After all, we have the James Webb Space Telescope. We have radio observatories that can detect signals from billions of light-years away. We have spectrographs capable of measuring stellar velocity shifts smaller than walking pace. Surely, with all of this, we can at least answer whether Proxima b is alive. That picture is almost entirely wrong. Here is what the optimistic summary leaves out. None of these instruments were designed to characterize the atmosphere of a planet 4.244 light-years away. The James Webb Space Telescope's coronagraph cannot separate Proxima b's light from Proxima's glare. The angular separation is too small and the contrast too extreme for the instrument's current design. Transmission spectroscopy requires the planet to transit its star, passing between us and Proxima. Current observations suggest Proxima b probably does not transit. Radio telescopes can detect powerful artificial signals, but they cannot detect the passive biosignatures: oxygen, methane, the infrared fingerprint of chlorophyll that would betray the presence of life in an otherwise silent world. The instruments we have built are extraordinary for the purposes they were designed to serve. For the specific purpose of answering whether Proxima b is alive, they are, at present, nearly blind. The absence is not nothing. If a civilization at Alpha Centauri were broadcasting radio signals in our direction at the intensity of our most powerful military radar systems, we would likely have detected them by now, given the decades of searching. The fact that we have not detected such signals either means no such civilization exists, or it exists and is not broadcasting toward us in the right way, or it is broadcasting in ways we are not yet capable of detecting, or we simply have not been listening at the right time or the right frequency. We cannot distinguish between these possibilities. Each is consistent with the observations. Each has radically different implications. Stop here for a moment. Take stock of where we are. We started with 2 points of light in the southern sky, familiar, dependable, ancient guides for sailors and navigators. And we have arrived here. A system of 3 stars, one of which almost certainly has a planet in its habitable zone, one of which may have planets in its habitable zone, and none of which have revealed their secrets to us, despite over a century of intensive observation. We have established that the nearest world to our solar system with any possibility of habitability is orbiting a violent, flare-throwing red dwarf. We have established that this world may or may not have an atmosphere, may or may not have water, may or may not be tidally locked in perpetual half-light and half-darkness. We have established that reaching it physically would require technology we do not possess and speeds we have never achieved. We have established that our searches for intelligent signals from the system have found only interference. And now, here is the question underneath all the other questions. Here is the one that, once you see it clearly, reshapes the entire picture we have been building. Is there life at Alpha Centauri? Not, could there be, but is there? Right now, as you listen to this, as the light from those two southern stars is falling on the dark side of Earth, as Proxima burns its quiet red flame 4.244 light-years away. Is there anything in that system that eats, breathes, reproduces, metabolizes, senses its environment, responds to it? Is there a microbe adhering to a mineral surface on the dark side of Proxima b? Is there a root pushing through something we would recognize as soil? Is there anything at all? We cannot know. And this is not the ordinary we do not yet know of science. The kind of uncertainty that a better telescope or a bigger dataset would resolve in the next decade. This is something more fundamental. This is the recognition that with our current technology, with our current understanding of physics, with the instruments we have built, and those we are now building, we cannot in principle answer this question in any definitive way. We cannot see Proxima b's atmosphere. We cannot analyze its chemistry from here. We cannot determine whether it has liquid water on its surface. The planet sits behind 4.24 light-years of vacuum, and the most we can do is stare at the faint wobble of its star and know that something is there, nothing more. What would it actually take to characterize Proxima b's atmosphere? In principle, if the planet transits its star, passes between us and Proxima during its orbit, we could use transmission spectroscopy. As the planet crosses the face of its star, some of the star's light filters through the planet's atmosphere, and molecules in that atmosphere leave characteristic fingerprints, absorption lines at specific wavelengths. By comparing the star's spectrum with and without the planet in transit, we can, in principle, read the chemistry of the atmosphere. This technique has already been used to detect atmospheric gases on planets orbiting other stars. The James Webb Space Telescope has used transmission spectroscopy to characterize atmospheres of planets hundreds of light-years away. Given this, why can't we do it for Proxima b? The answer is geometry. For a planet to transit its star from our perspective, its orbital plane must be aligned with our line of sight. For Proxima b, the probability of this geometric alignment occurring by chance is roughly 1.5%. Observations of Proxima's brightness looking for the tiny dimming that would indicate a transit have found no evidence of transits. This does not definitively rule them out. The transit signal would be small, and the star's own variability from flares makes detecting subtle dimmings difficult. But the best current evidence suggests Proxima b probably does not transit. If it does not transit, transmission spectroscopy using any instrument currently planned is not available to us. Direct imaging, actually photographing the planet, separating its reflected or thermal light from the star's overwhelming glare, would require suppressing Proxima's light by a factor of roughly 10 billion, while maintaining the angular resolution to separate a planet that is only a fraction of a second of arc from the star. The James Webb Space Telescope cannot do this. The Nancy Grace Roman Space Telescope may eventually have relevant capability for some targets, but the specifics for Proxima b remain uncertain. What if there is life at Alpha Centauri? Not just microbial life, but complex life, even intelligent life. Would we know? Can we even design a signal that would be unmistakably biological? Could the James Webb Telescope, staring at Proxima b for 1,000 hours, detect the spectral signature of chlorophyll, of oxygen produced by photosynthesis, of methane in disequilibrium with an atmosphere? Not yet. Not with any instrument in operation or in development as of current knowledge. Could a radio signal from Proxima b reach us? Yes. Radio waves travel at the speed of light, and 4 light-years is not enough distance to meaningfully attenuate a powerful radio signal. But we have been listening, and we have heard only our own voices. Is there something fundamentally wrong with our search strategy? Are we listening on the wrong frequencies, at the wrong times, with the wrong assumptions about what intelligence looks like and how it chooses to communicate? Is it possible that the silence is the answer? That Alpha Centauri is simply empty and the universe around us is simply quiet, not because of detection limitations, but because there is genuinely nothing there to detect? Is it possible that the opposite is true? That something is there and it knows we are here, and it has chosen silence for reasons we cannot fathom? Can we be sure that life and intelligence, as we define them, are the right concepts to apply when thinking about what might orbit Proxima Centauri? Could there be forms of complexity there that would not register on any instrument we have because we have defined life too narrowly? What does it mean that our nearest stellar neighbor has presented us, for the first time in history, with a specific place, a named star, a measured distance, a planet with a calculated mass and an orbital period, where the question of whether we are alone might, in principle, be resolved? And beneath all of this, what does it mean to live in the moment when the abstract becomes specific? For the entire history of science, the question, is there life elsewhere in the universe, has been purely abstract. It applied to everywhere in general and nowhere in particular. There was no address. There was no coordinate. There was no specific target that the question pointed to and said, here, ask it here. This is where the answer might live. Now there is. Proxima Centauri, B, 4.244 light-years away. Minimum mass 1.27 Earths. Orbital period 11.2 days. Situated in the habitable zone of the nearest star to the Sun. This is the address. For the first time, the abstract question has a specific, named location, and we still cannot answer it. Once you see this, once you feel the weight of that specific coordinate, the entire picture of Alpha Centauri inverts. It is no longer merely an interesting astronomical object. It is not merely the nearest star system. It is the one place in the observable universe where the question of our cosmic loneliness is most precisely posed and most stubbornly, presently unanswerable. It is the place where the universe has offered us our best chance at an answer, and then placed that answer behind a wall of distance and technical limitation that we cannot yet breach. Not a wall that physics forbids us to breach, just one we haven't broken through yet. The question has been made specific. The answer has not yet arrived. Stand somewhere, for a moment, where the horizon is wide and the sky is dark. Imagine a field, or a hillside, or the deck of a ship somewhere south of the equator. Anywhere that the sky opens up fully and the atmosphere thins enough that the stars burn with the particular steadiness they have on clear nights. The Milky Way is overhead, a river of light too dense to resolve with the naked eye alone. And there, near the bottom of the southern sky, are the 2 stars you have been learning about. Alpha Centauri A and B burn together, close enough that in ordinary conditions they appear as one, like a lamp left on in a distant window. They are, astronomically speaking, almost beside you. On the scale of the galaxy, which spans roughly 100,000 light-years and contains somewhere between 200 and 400 billion stars. Alpha Centauri is your next-door neighbor. It is the stellar equivalent of a house you can see from your front porch. You have been looking at that house for your entire life, and for every life that came before yours. For all of recorded human history, those stars have been visible to anyone in the southern sky. The sailors of ancient Polynesia used them. The Aboriginal sky watchers of Australia charted them, building astronomical traditions that stretched back tens of thousands of years before Western science categorized the stars they described. Every civilization that existed below the equator knew those stars by whatever name they gave to that part of the sky. They did not know what we know now. They did not know that the brighter of those 2 points of light is actually 2 stars locked in an 80-year orbital waltz. They did not know that a third star, faint, red, invisible without a telescope, is technically even closer, the actual nearest star to our sun. They did not know that around that faint red star, a planet circles every 11.2 days in a zone where the temperature could permit liquid water. They knew only the light. They trusted it. They navigated by it. They told stories about it. There is something profound in that long human relationship with those stars, in the way they meant navigation before they meant anything scientific. The star that might harbor life, the star around which a rocky world orbits in the warmth, was a guide long before it was a question. People found their way home by its light, not knowing that the light was coming from something that might, in some other configuration of chemistry, be a home itself. The human relationship with Alpha Centauri goes back further than written records. In some Aboriginal Australian astronomical traditions, the area of sky around Centaurus is associated with narratives about the cosmos that are among the oldest continuous astronomical knowledge systems anywhere on Earth. In these traditions, the stars are not inert objects, but participants in stories, entities with histories and relationships, and meanings that predate anything we would call science by an enormous margin. This is not to romanticize pre-scientific knowledge at the expense of what careful measurement has revealed. What careful measurement has revealed is extraordinary. The parallax measurement Thomas Henderson made in 1839, working at the Cape of Good Hope with the instruments of his time, gave us the first real number, how far away those stars are. That number opened everything else. It placed Alpha Centauri in space, gave it a location, made it something real and not just luminous. But there is something in that long pre-scientific relationship with those stars that the measurements cannot quite capture. The simple, unmediated experience of looking at them, of standing under the dark sky and knowing, or even not knowing, just feeling that the light entering your eye left those stars 4 years ago. What you are seeing is not the present state of those stars, but a 4-year-old message, a dispatch from the recent past, traveling at the fastest speed the universe allows. By the time their light reaches you, whatever they are doing right now, whatever stellar flares are erupting, whatever storms are crossing the face of their hidden planets, whatever chemistry is unfolding in whatever atmosphere those planets might have, is already 4 years old, and the news of it has not yet arrived. We are always reading old light. Every star we see is a message from the past. Alpha Centauri's message is 4 years old. The most distant galaxies visible with our best telescopes are delivering messages that are 13 billion years old. We live, always, in a kind of cosmic time lag, seeing the universe as it was rather than as it is. And there is something meditative in that, something that deserves to be sat with, rather than immediately resolved into explanation. The question of what Alpha Centauri looks like right now, what its planets are doing, what its stars are flaring, what its hidden worlds are experiencing, is not only a question we cannot answer because the instruments don't exist. It is a question we cannot answer because the information doesn't exist here. The current state of Alpha Centauri will not arrive for 4 more years. We are always 4 years behind. And this is not a special limitation of our distance from Alpha Centauri. It applies to every star, every galaxy, every photon that has ever reached our eyes. The universe we see is the universe's past, sent to us at the speed of light, arriving in the present moment to describe a history. The humility this requires is not a small thing. It means that all of our astronomical knowledge, every spectrum, every measurement, every carefully inferred property of every star and planet ever studied, describes how things were, not how they are. The universe's present is always elsewhere, and by the time it arrives to us, it will be the past. This applies to Proxima b with particular weight. If there is life on Proxima b, if there has been a biosphere there for 1 billion years, filling an ocean with organisms, developing complexity, reaching toward whatever it reaches toward, then photons carrying evidence of that life have been traveling toward us for 4.244 years. Some of those photons are in transit right now, passing through the interstellar medium between here and there, and they will arrive. And if we had the instruments to read them, which we do not, we could know. Not the present state of that biosphere, but its state 4 years ago. And 4 years ago, nothing about it would have changed in ways we could detect. The universe is generous with its information. It sends light from everything, in all directions, without restraint. We are simply not yet equipped to read most of it. There is a different kind of navigator worth thinking about. Not the Polynesian wayfinders who used stars to cross the Pacific, though we will return to them. The navigators to think about now are the astronomers who made the measurements, who built the instruments, who chose to point their telescopes at a faint, unassuming red star in 2016 and stared at it for months, watching for the 1.38 meter per second wobble that would mean a planet. Those people, Guilherme Anglada Escudé and his collaborators, were doing something that no generation of humans before theirs could do. They were measuring the presence of a world they would never see. They would never see it directly. They would never stand on it, touch its surface, breathe its air, or know with certainty what it looked like. They would know it existed by what it did to its star, by the shadow it cast on the light of a sun 4 light years away, and that would be the entirety of their contact with it. They found a world through a walking pace wobble in starlight, and they named it, and the world celebrated. And then the data sat in scientific journals, and the planet remained as invisible and unreachable as it had been the day before the announcement. This is one of the most remarkable things about the current age of astronomy. We have found thousands of worlds. We have named them, catalogued them, estimated their masses and orbital periods, and approximate temperatures. We have found them in habitable zones, and outside them, around young stars and old stars, around solitary stars and binary stars. And we have not been to any of them. We have not sent anything to any of them. We have not come within remotely sensible proximity to a single one. We are like navigators who have charted coastlines they cannot touch, like surveyors who have mapped mountains they cannot climb. We have discovered a universe of worlds through inference, through the grammar of light and gravitational whisper, and none of those worlds have ever felt the weight of a human footstep. The historical parallel this calls to mind is not the age of European exploration. Those voyages were motivated by conquest as well as curiosity, and their consequences for the peoples encountered were frequently catastrophic. A better parallel is the age of theoretical cartography, the centuries before anyone sailed to discover whether the continents on the map were real. Medieval scholars who debated whether there was an Antipodean continent, a great southern land to balance the northern landmasses implied by geometric symmetry and hinted at by travelers' reports, had drawn maps of something they had never seen. They had reasoned it into existence from principles. Some of their reasoning was wrong, and the continent they imagined was not quite what Australia and Antarctica turned out to be. But they were doing something fundamentally human, extending their minds further than their bodies could go, making sense of a world they could not directly experience. We are doing exactly the same thing with Proxima b. We have reasoned it into existence from the wobble of a star. We have debated its properties through models and simulations run on computers. We have argued about whether it has an atmosphere, whether it has water, whether it is habitable, whether it could be inhabited. And all of this argument has been conducted without a single direct observation of the planet itself. We are cartographers of the unreachable. But here is the difference, and this is where the existential weight truly settles in. The southern continent turned out to be real. The voyages eventually happened. The Terra Australis Incognita was found, mapped, explored, inhabited. The distance between theory and reality was eventually collapsed by ships and people and time. For Proxima b, even on the most optimistic timelines available to us, the collapse of that distance is a multi-generational project. The fastest conceivable probe, under the breakthrough starshot concept, would take 20 years to arrive and 4 years to transmit its data home. 24 years minimum, and that assumes technology that does not yet exist. A crewed mission under any currently plausible propulsion system would take centuries or millennia. The people who planned such a mission would not live to see it arrive. The civilization that sent it would be unrecognizable by the time it returned data. This is not a reason for despair, but it is a reason for a particular kind of seriousness, a gravity that belongs to questions whose answers outlast the people asking them. What does it mean to ask a question you know you will never personally see answered? What does it mean to build instruments and fund surveys and train graduate students in the direction of a question whose resolution lies decades or centuries away? This is not hypothetical. This is what the researchers working on Alpha Centauri are doing, and they know it. They are not working toward a personal revelation. They are working toward a generational one. They are planting seeds in soil they will never stand in when those seeds bloom. The Polynesian navigators of the Pacific, the wayfinders who crossed thousands of kilometers of open ocean using stars, waves, birds, and the feel of swell beneath the hull, navigated not just to where they were going, but into the unknown. The most extraordinary journeys in that tradition were voyages to places no living person had been, using knowledge assembled across generations in vessels that could not turn back once committed to the open sea. The navigator who set out for what became Hawaii, sailing northeast from the Marquesas Islands into waters no one had yet charted, was operating entirely on inference, on accumulated knowledge, on the courage to trust that the principles had been correctly understood, even when no one had confirmed the destination. The stars above were real. The physics was real. The land, when it appeared after weeks of open ocean, was real, just as predicted. We are pointing instruments at a star that might have a living world, trusting that the principles of physics and chemistry have been correctly understood, trusting that the wobble in the radial velocity data means what we believe it means, trusting that the habitable zone models are approximately right, trusting that whatever is there will eventually reveal itself to a technology we haven't yet built. The question underneath everything, the one that makes all the science feel not merely interesting but urgent, is whether this universe is the kind of universe in which life is common, or rare, or singular. If it is common, then Proxima b is almost certainly alive with something, microbial at minimum, and possibly more. If life is rare, then Proxima b may be a barren stone, and the closest living world may be the one you are standing on. And if life is singular, if the improbable concatenation of events that gave rise to Earth was a truly unique accident in an otherwise sterile universe, then we are the only life that exists, and we are staring at a lifeless star system that will never stare back. We cannot, right now, distinguish between these possibilities with any amount of data currently available to us. We do not know. This is not a comfortable position for a curious species to occupy. It is, however, the honest one. It means that Alpha Centauri is not merely an astronomical curiosity. It is the first test case. For the first time, a specific named measured star with a specific named measured planet is presenting us with the question of cosmic loneliness at a precise address. Not abstractly everywhere, not metaphorically anywhere. Here, 4.244 light-years, in the habitable zone. We are looking right at it, and we cannot tell. The human moment this creates is extraordinary. We live at the hinge point, the generation that has found the nearest potentially habitable world and does not yet have the means to know what it is. We are post-discovery and pre-knowledge. We know enough to ask the question precisely and not enough to answer it. This is an uncomfortable position, but it is also, in its own way, a gift. The question is open. The universe has not yet declared itself empty. Nothing has been ruled out. Whatever is true about Proxima b has been true for billions of years, waiting in patient silence while a small species on a small planet 4 light-years away slowly, painstakingly, built the instruments to ask. Every night from the southern hemisphere, those stars rise and set. They have been rising and setting since before human civilization existed. Whatever is in that system, whatever is happening on the surface of Proxima b right now, in the 4-year-old news currently in transit toward us at the speed of light, has been going on for a very long time without our knowledge, and will continue for a very long time beyond our current ability to understand. The silence from 4 light-years is not a verdict. It never has been. Go back to the beginning. Go back to those 2 points of light in the southern sky, the ones that ancient sailors trusted with their lives, the ones that have been rising and setting over human civilization for as long as there has been human civilization to observe them. They are still there. They will be there tonight if the sky is clear and you are somewhere south of the equator, or high enough in the northern latitudes to catch them near the horizon. The light arriving now left those stars 4 years ago, when you were doing something else entirely, when whatever was happening on Proxima b, whatever chemistry or stillness or warmth or cold was present on that orbiting world, was already in the past and already sending its news toward you at the speed of light. What we know now that no one knew before, not when Henderson made his measurements at the Cape of Good Hope in the 1830s, not when Innes photographed his plates in Johannesburg in 1915, not when the first telescope resolved the 2 stars of the binary into 2 separate points of light, is that the universe nearest to us is complicated and structured and possibly alive. We know it has 3 stars, not 1. We know the nearest of those stars has at least 1 planet, circling it every 11.2 days in the warmth that could sustain liquid water. We know that the same star is violent, explosive, magnetically hyperactive. A flare star that bathes its planet in ultraviolet storms intense enough to strip an atmosphere. We know the planet may or may not have an atmosphere to strip. We know the planet may or may not be tidally locked. We know we cannot answer the most important question about it, not with any instrument currently built or currently planned. We also know something about ourselves that we perhaps did not know before. We know that we are the kind of species that finds a 1.38 meter per second wobble in a star 4 light years away and calls it a planet and names it, and immediately asks what it might be like to stand on it. We are the kind of species that builds spectrographs in the desert night of the Atacama, in the high, dry air above Chile, and stares at red stars for months, watching for signals of life in data that is mostly noise. We are the kind of species that, upon finding a planet in the habitable zone of the nearest star, immediately begins arguing about how to get there. This impulse, the impulse to look, to reach, to ask, to measure, is not new. It is as old as the first person who looked at those stars and wondered what they were. The tools are new, the precision is new, the scale of what we understand is entirely new. But the looking itself, the pointing of attention outward from this small planet toward those small lights, is as ancient as human consciousness. There is a kind of melancholy in what we have found and what we have not found. We have found a planet in the nearest star system, something that seemed almost too convenient to be true, and yet appears to be true. But we have not found evidence of life there. We have not found a signal. We have not found a biosignature. We have found a world that might be anything: a scorched stone, a frozen desert, a global ocean with no land, a world wrapped in alien clouds and inscrutable chemistry, or, and this is the possibility that makes all the rest matter, a world with something alive on it. The silence from 4 light years is not a refusal. It is simply the universe being what it is, large, old, and indifferent to our timetable. Whatever answer is waiting in the data that will arrive over the coming decades, from the extremely large telescope, from future space missions, from techniques we haven't yet conceived, will come when it comes, not when we want it to. And this is where the mundane becomes something close to sacred. Those 2 stars in the southern sky, the ones that look to the naked eye exactly as they looked to every generation of human beings before us, now carry a weight of meaning that no previous generation could have fully articulated. They are not just stars. They are not just navigation guides, though they remain that. They are not just the nearest stellar neighbors, though they are that too. They are the address of a question. The specific, named, measured location of the most profound inquiry the human species has ever formulated. Are we alone? We have been asking that question abstractly for centuries. We have projected it outward into the cosmos in a general way, pointing at the whole sky and wondering. But now the question has a street address. It has a distance. It has a planet with a measured mass and an orbital period and a calculated position in a habitable zone. The abstraction has become concrete, and the question has become, for the first time, genuinely answerable in principle. Not in practice, not now, perhaps not in our lifetimes, but in principle. That is what Alpha Centauri is hiding. Not merely 3 stars instead of 1. Not merely a planet instead of an empty system. It is hiding the answer to the oldest question, behind 4.244 light-years of light-speed delay and technical limitation and cosmic patience. Those stars are still out there, still burning. They were burning when human civilization began, and they will be burning when it ends, and they will burn for trillions of years after everything we have ever built has dissolved into cold and dark. And if there is anything on the world that orbits the nearest of them, if there is any form of chemistry there that has arranged itself into something that can perceive and respond, and, in some formulation, we might or might not recognize as awareness, look outward and wonder, then for all of that vast duration, there will have been two places in this small corner of the galaxy where something looked up at the stars and asked. If this changed how you see those two stars the next time you find them in the sky, then the time was well spent. Thank you for staying with this.